Hi, I am Shahnawaz. In this lecture, we will study monoids and semigroups, and we'll see that we can view a category with single object as a monoid and vice versa. So we'll first start with a few definitions. So we have the first definition of a semigroup. So we say a semigroup is actually a set together with an associative binary operation. So a semigroup is actually a set, say S, which is equipped with uh, a binary operation which is associative. Together with an associative binary operation. I mean, we know this binary operation by n. So this is a function from s times s to s, which takes a pair, say st, to the element st. So one can note that st may not be equal to ts. So note that st may not be equal to ts in general. So for if st is ts for all s and t in s, then we say the binary operation is commutative. Then we say that this s is a commutative semigroup. So then s is called a commutative semigroup. So now let us define what do we mean by a monoid. So a monoid is actually a semigroup that contains an identity element. So a monoid is a semigroup that contains the identity element. Let us note by the identity element by E that contains an element let us note the semigroup by S. So a monoid, say M, is a semigroup that contains an element, say E, such that S times E is same as S, which is same as E dot S. So this is true for all S in M. So this element E, this is called the identity element of M. So the element E is called the identity element. So for example, if we consider this set of positive integers, then that is a monoid. So we have an example. So the set uh, z plus, I mean the set of positive integers Z plus is actually a semigroup. So this is a semigroup, and this set. So this is a semigroup with respect to addition as a binary operation. So with respect to addition as the binary operation. However, if we include 0 with this set, then we get a monoid. So, however, this set of positive integers included the 0 element is a monoid. Now we have the definition of a monoid homomorphism. So, a monoid homomorphism between two monoids is actually a map that preserves the identity element and the binary operation. So let m and say m prime be two monoids. Then a map say f from m to m prime is called a monoid morphism, monoid homomorphism. If so, we have two items. If f preserves the identities, that is f of the identity on m, that is denoted by that by e sub m. So it has to be equal to the identity of m prime, that is denoted that by e m prime. So where e sub m and e sub m prime are the identities of m and m prime respectively. So second is that this f preserves binary operations. So f preserves binary operations, i.e. Uh, for all say m and n in m, f of m dot n is f of m dot f of n. So this is what we call uh, a monoid homomorphism. Now, mm, if we are given any set, so we can construct a monoid. Say suppose we are given a set A, then we can construct a monoid on A. I mean a monoid which is determined by A. So for that we first define the clean closure. Let us define the clean closure. So let us consider a set A. So then the clean closure of the clean closure say A star of A. So this is actually the set of all lists of the elements of A, but of finite length. So then clean closure of A is the set of all strings, or sometimes we call these strings as lists. So or they are called lists, uh, or sometimes we call these strings as words. So this clean closure contain all the strings or lists of finite length of elements of A. So we can write these lists in brackets, in parentheses. So this is the notation. So we can write these lists in parentheses. Um, for example, let A be the set consisting of four elements, say small a, b, c, and d. Then, if we consider this list, say d, a, b, a, c, so this is a list of length 5. So this is in the clean closure. So this A star includes the empty list as well. So A star includes, it includes the empty list, and we denote the empty list by these two brackets, these two parentheses. So it includes this list as well, and the length of the empty list is 0. And for any for any element, say a in A, this A star contains the the list of length 1. So then, and for any A in A, uh, A star contains the list A as well. So this gives us an inclusion from A to A star, where we can identify an element A in A with the list A in A star. So, so remark. So there is an inclusion, say I from A into A star, which takes an element A in A and maps it to the list A. This A, um, so we call this A star. So this A is the generating set of A star. So A is called the generating set of A star. Now we actually want to construct a monoid with given any set. So now we have this set A and we have the notion of the clean closure. Now if we define a suitable binary operation on A star, this will give us a monoid on A. So and that those monoids are called the free monoids. So we have the definition. So let A be any set. So one should note here that if A is non-empty, then this A star is always an infinite set, because so let us write this down here. So if A is non-empty set, then A star is always an infinite set. So this is true even if this A contains just a single element. So if A and there is just a single element in A, I mean if A is just this singleton set, then A star contain all the list of the form. So first of all we have the empty list, then the list of length 1, list of length 2, similarly list of length 3, so on. So let A be any set and A star B it is clean closure. So let A star B it is clean closure. Uh, so now we will define a binary operation on A star. So define map, I mean define a binary operation on A star as, so we take an element in A star, let us take a list say of length n and a list say of length m. Let us call this b1 up to bm. Then we define this product. So this gives us a list of length n plus m. So this is in some sense the concatenation of these two elements. So this is sometimes called the concatenation. So actually we are gluing these two lists. So this is the list of length n plus m. So this is again of finite length, hence this is in A star. So this is a binary operation on A star, and the empty list serves as the identity element on A star. So then A star is a monoid with the identity element, the list of length 0, which is the empty list. Now this binary operation is makes A star into a monoid, and we call this monoid a free monoid. So hence A star together with the binary operation, which is the concatenation. This is the concatenation. Is a monoid determined by A. And is called the free monoid on A, denoted by FA. Now, defining these free monoids, we have a universal property on free monoids. So, this is the universal property of free monoids or monoids. So this is actually a proposition. It states that. So let us take any set A. So let A be any set. So one should note here that F A and A star. So as such they are equal, but FA is A star equivalent with this binary operation. So as such they are the same sets. So let A be any set and let I be the inclusion of A into the free monoid of A. So should be the natural inclusion. So then given any function, so let M be any monoid and say F be any map from the free monoid on A to monoid M. So if this is the case, then this F induces a unique homomorphism from A to M. Sorry, this is actually a map from A to M. So let F be a map from A into M. Then F induces a unique homomorphism. Let us call that F tilde from Fa to M, such that the diagram, so we have this diagram here. So we have Fa here, we have the natural map, the inclusion, let us call this I, and we have a monoid M here and a given map, say F. Then we say this F induces a unique homomorphism F tilde from Fa to M. That is this diagram commutes, such that this diagram commutes. I.e. F tilde composed with I, which is a map from A to M, is same as F. Let us prove this. So we first define F tilde. So define F tilde a map from the free monoid on A to M as, so this F tilde takes the empty list in A, which is just the parenthesis. So it maps it to the identity of M, because M is given to be a monoid, so it has the identity element. So EM is the identity of M. And if we have any list in F of A, say we have a list, suppose of length n, so it takes this list to the element fa1 fa2, where between fa1 and fa2 we have the binary operation of M, because M is a monoid, so M is having a binary operation. So this is up to f of an. So one can see over here this makes sense. So mm, so by defining f tilde this way, we can note that. So we can note that then for all a in a, we have, so if we look at f of the element a, now f of a is an element in M, but we can view f of a as f tilde of the element a. I mean, we can view this f of a as f tilde of list of a. So this is same as f tilde of, now the list of a, since I map is the element a to the word of length 1, so this is I of a, or this is f tilde of I of a. So that is, so that is f tilde of I is same as the map f. Now we want to prove that this f tilde is a homomorphism. So now to prove f tilde is a homomorphism, let us take two elements in and the free monoid over A. So let a1 up to an and b1 up to bm be two elements in the free monoid on A. So to prove this is f tilde is a homomorphism, we have to prove it preserves the binary operation. So we have f tilde of the list a1 up to an, then we had a binary operation which is the on concatenation, and then we have the list b1 up to bm. So this is same as f tilde, and now evaluating this binary operation, we get a list of n plus m symbols. So we have these n symbols a1 up to an, then b1 up to bm. So this is the list of m plus m symbols. Then by definition of f tilde, it is the map, it is the element fa1 fa2 up to fam, then fb1 up to fb2 up to fbm. So this is same as f tilde of the list a1 up to an and f tilde of the list b1 up to bm. So this proves this f tilde is a homomorphism. Now to prove it is uniqueness, let us suppose so therefore f tilde is a homomorphism. Now to prove the uniqueness, let us assume that there is some another map. So say g tilde from fa to m be another such homomorphism. Such that, so be another homomorphism such that g tilde composed with the map I is the map f. So what we are saying here, we are saying that we are having, we say that suppose there is one more map g tilde such that this diagram commutes, I mean G tilde composed I is F. Then we have to prove G tilde and F tilde are actually the same map. So, so this means, so that is uh, G tilde of the list A is same as F of A for all A in A. So, so then if this is the case, then if we look at G tilde of the list A1 up to AN, so then by definition of G tilde, so G tilde being a homomorphism, this is G tilde of A1 up to G tilde of AN. But G tilde of the list is F of A, so this is F of A1 up to F of AN. By definition of F tilde, it is F tilde of A1 up to AN. So this proves F tilde is unique because G tilde and F tilde are same. So this proves F tilde is unique. Now with this property, we have a proposition here. It states that, so the proposition is like this. So let us consider two free monoids. So let M and N be free monoids on A with, suppose we had the natural inclusions from A to M given by I, and say J from A to N. So these are the natural, they are the natural inclusions. So then there exists a unique isomorphism, monoid isomorphism. Let us call that H from M to N, such that if we compose H with I, we get the inclusion J, and H inverse composed with J is the map I. So this is what we have to prove. So let us prove this. Now we are going to use the universal mapping property. So this is the universal mapping property. I forgot here to write this. This is the universal mapping property. So let us prove this. So since M is a free monoid on A, so since M is a free monoid on A, then by universal mapping property, we have we have for the map, we have for the map J, which is from A to N, the following commutative diagram. So we are given a free monoid M, and A is it is generating set, and this is the natural inclusion I. So we consider a monoid N here. So we just forget N is free. Let us uh, assume N is just a monoid. Then we are given that I is a map from A to N. But then by universal property, so this is the map J here. So then by universal mapping property, for this map J, we have a unique homomorphism J tilde such that this diagram commutes. So that is uh, J tilde composite I is the map J. Similarly, N being free, I mean, if we switch the roles of M and N, because M and N are both given to be free. So similarly, by switching the roles of M and N, so we forgot to mention here this J tilde is unique. So by switching roles of M and N, there exists a unique homomorphism I tilde such that, so this I tilde is from N to M such that uh, I composite J I tilde composite J is the map I. So now let us consider the following diagram. Now consider the diagram. So we have this diagram here. So we have M here, then we have N here, and again we have M here. So we have A here. This is the inclusion I. This is the inclusion J. This is the inclusion I. This is the map J tilde here, and this is the map I tilde. So now if we look at this composition, so this is the composite map I tilde composite J tilde. So that means we have this diagram here, M to M, then we have A here, this is the map I here, this is the map I here, this is the map I tilde composite J tilde. So now M being a free monoid and this I being the inclusion map, then for this I, this induces a homomorphism from M to M. But we also have a homomorphism from M to M, which is the identity morphism. That means this map is actually the identity morphism on N, because uh, there's a unique homomorphism from M to M, which is induced by I. So now we are given two homomorphism from I M to M. So by uniqueness, they have to be equal. So by considering this diagram, so then uh, I tilde composite J tilde from M to M is the unique homomorphism such that this diagram commutes. I mean, this diagram commutes. So that means uh, I tilde composite j tilde composite I is same as I. That such that I tilde composite j tilde composite I is the map I. But the identity morphism on but the identity morphism on morphism from homomorphism from M to M, but this is also a homomorphism. So this shows that I tilde composite J tilde is the identity map on M. Similarly, by switching the rules of M and N, we can prove that J tilde composite I tilde is the identity map on N. So similarly, by switching the roles of M and N, we see that J tilde composite I tilde is the identity map on N. So if we let this map J to be equal to the map H, so put H to be equal to the map J, then we have the following uh, observation. So actually this implies here that J tilde is the inverse of I tilde and I tilde is the inverse of J tilde. So that means uh, so we have H composite uh, I is J and H inverse composite J is I. So this proves that the map H is an isomorphism. So one should note here by isomorphism we mean a bijective homomorphism, since H is a homomorphism with inverse H inverse. So this would imply that H is an isomorphism. So this would imply these M and N, they are isomorphic. So this proves the result. Now we can view this monoid as a category. So this is monoid as a category. So any monoid, say M, this determines a category. Determines a category, and we usually denote such categories by CM. That means the category determined by monoid M. So this category has the object class. So the object class of category of M has one element, which we will denote by star. So this star is any arbitrary element. So a simple uniform choice is to take star equal to M. So a simple uniform choice is to take star to be the monoid itself. So that means this category M has just one object, and let us take the object M. Now the arrow class of the category CM is are the elements of M. So the arrows of M are the elements of M with star as the source and target, with star as the source. By source we mean the domain, and target we mean the codomain. So that since this category has only one object star, so any element in M, let us take F to be an element in M. So this F uh, determines an arrow between star to star. So any element in the monoid M can be identified as a map from the only object of the category to itself. Similarly, the composition is the binary operation on M. So composition is the binary operation on M. That is, if F and G are two elements in the monoid M, then they uh, can be viewed as the arrows between uh, the object of the category CM. So then this F is an arrow between star to star because this category has only one object which we denote by star, and then we have the arrow G which is again between star and star. So from this star to star we have this composition G composite F. Now F being an element of M, G being an element of M, so naturally GOF is also an element of M, and we do not define this composition to be the binary operation of M. So where G composite F is G dot F, where dot is the binary operation on M. So that means this monoid CM is a. So the question is like this. So we see that if we have a monoid M, so using this monoid we can construct CM, which is a category with one object. Now the question is like this: if we have a category with one object, can we identify that category with a monoid? And the answer is yes. So this is if and only if. So if we have a category with just one object, then that category can be identified as a monoid.